students and other invitees to this online seminar on super heavy elements. As you know, this is a long-standing activity of KPA. We have been doing this since October 2023 for the benefit of our members and students. Our main objective is to inform our members and students about developments in various fields in the easiest possible way, that is the online mode, so that they will learn, pick up ideas and information about different fields which they might not have heard before. So that this will contribute to their overall education in the field of physics and other allied aspects, other allied disciplines. So we have been helped in this endeavor by faculty members from colleges, universities, and institutes. Very graciously, they have given their time and effort. So we are very thankful to them. So we have also conducted these seminars in Kannada also with the objective of encouraging the usage of Kannada in higher education. They are very essential so that because communication improves between teachers and students, that is our objective. And the new education policy also suggests that the language should not become a barrier in communicating scientific ideas, technical ideas between students and teachers. So we have all experienced the problems our students, our teachers face in communicating in an English language, okay, which of course nowadays is a practical necessity, but ultimately, if you want to be self-reliant, we have to switch over later on. I don't know when it's possible. So today we have a distinguished speaker from government college, government first grade college, Devanahalli, Professor Dr. S.C. Manjunath. So he will speak about super heavy elements. He will speak for about 50 minutes, followed by 10 minutes of question answer session. So before I request him to speak, I request our Joint Secretary, Dr. Rudraswamy, to introduce the speaker. Over to you, Dr. Rudraswamy.
Thank you, sir. Thank you very much, sir, for this great opportunity. It is indeed a great honor and immense pleasure to introduce Dr. Manjunatha HC, who is presently serving as Professor of Physics in Government First Grade College, Devanahalli, Bangalore Rural District. He obtained his PhD degree in 2013 from Bangalore University under my guidance. He has guided many teaching faculties and students to get their PhD degrees and presently leading Kolar Physics Research Group. He has immensely contributed for all-round development of nuclear physics research and won several prestigious awards such as Seed Money to Young Scientist Award in 2013 constituted by Government of Karnataka, Dr. Tarun Datta Memorial Award in 2018 constituted by Indian Association of Nuclear Chemists and Allied Scientists, Sir C.V. Raman Young Scientist Award in 2021 constituted by Government of Karnataka, Kannada Rajyotsava Award constituted by Kolar District Administration. His name was figured out in the list of world top 2% scientists 2021 among nuclear scientists announced by Stanford University, USA. He won several times Best Research Paper Awards in the year 2012, 17, 18, 22 in various nuclear physics symposia. He has published nearly 490 research papers, both in national and international journals and proceedings, 9 physics books, and 1 book chapter. He has delivered many invited talks in national conferences and refresher courses. So with this brief introduction, I cordially invite Dr. Manjunath to speak on super heavy elements. Over to you, Dr. Manjunath, and thank you very much.
Thank you very much, sir. Thank you for your nice introduction, and I thank to this Karnataka Physics Association for giving this opportunity to share the information regarding the super heavy elements. So this is what the activity we are doing since last 2015. It is around we started this work almost 10 years back. We started before that. I was working in the radiation physics background, and now the whatever the work we did in our labs, just a brief information I'm going to share here. So since it is a 50 minutes talk, I have planned the my talk like this: a brief introduction about the super heavy elements, and then the failure of these fusion reactions to synthesis the super heavy elements, and then the important the reason for the failure, that is the optimal energy concept I'm going to introduce here, and then these few entrance channel parameters and the deformations parameters which are responsible for the failure of these reactions, and then the super heavy elements radioactive decay properties. Finally, the ends my talk with the summary. That is how I planned for the 50 minutes. So see, this is the periodic table published by IUPAC in the year 2023. Even today, this is not yet changed. So in the periodic table, the here the arrow mark shown here, this is actually super heavy elements. Usually the elements with the atomic number greater than the 103 are termed as super heavy elements. So heavy is there and super heavy is there. Heavy means usually up to the actinides, and behind the actinides it is called as the super heavy. It is also called as sometimes transactinides. Transactinides. All these super heavy elements are the synthetic elements. So these are synthesized through the fusion reactions. So actually here there are two types of the fusion reactions. One is the cold fusion reactions, and other one is the hot fusion reactions. So up to the element 113, the super heavy elements were synthesized using the cold fusion reactions, and above 113, so up to the 118, the elements were synthesized through the hot fusion reactions. So now the people are trying to extend the periodic table beyond the 118 also. So coming to the what is the cold fusion reaction and what is the hot fusion reactions? So cold fusion and hot fusion reaction based on the type of the projectile and the targets. If you use the calcium as the projectile and the actinides as the targets, then that is simply called as what the hot fusion reactions. And if you use any projectile and with the targets lead and the bismuth, then that is the termed as the cold fusion reactions. So the one more difference between the cold fusion and the hot fusion is the excitation energy. Here in the cold fusion reaction, compound nucleus formation takes place around the near to the 20-25 MeV, whereas in the hot fusion reactions, the compound nucleus takes place at the excitation energy around the nearly 35 to 40 MeV. So excitation energy is the important difference between the cold fusion and the hot fusion reactions. So if you see this figure, just you can how this cross section varies with the atomic number. As this atomic number keeps on increases, the production cross section decreases. The blue curve shown here is the production cross section of the cold fusion reactions. Usually, the evaporation residue is formed in the 1N and 2N channels for the cold fusion reactions. This is the production cross section shown for the 1N channel. So as this atomic number increases, it falls, this curve falls, and it becomes very small when it comes to the 130. So that is the last element synthesized through the super heavy, these cold fusion reactions. And whereas these hot fusion reactions, up to the 110 it decreases, and beyond that this production cross section increases. This curve is very important because the production cross section decides the time of the synthesizing the super heavy element. So actually, who is she? She means super heavy elements. So 110, 112, to up to the 118. These elements were synthesized in the reputed international accelerator centers. So this 110 is 110 to 110, 11, 12. These elements were synthesized in the Germany. And this Russians synthesized the 113 to the 118. Russians are very much interested about the extending the periodic table. Even today they are struggling to extend the periodic table. So Japan synthesized one element, super heavy element, and added one element to the periodic table. That is 113. That is nihonium actually. So this is this is just a different labs which were involved in the synthesizing the super heavy elements. Berkeley lab of USA is involved, and this Dubna USS Russia Dubna this accelerator center also involved in the synthesizing the super heavy elements like 114, 116, 113, 115, 118, 117. And Darmstadt of Germany is also involved in the 118, 109, 118, and 110, 111, and 112 under the captainship of the Hoffman. And Riken is also, Japanese Riken laboratory is also involved in the synthesizing the super heavy element. They repeated the synthesis of the 110, 11, 12, and newly synthesized the element 113. And Ganil is also involving in the synthesizing the super heavy elements. So the present limit of the periodic table is the 118. Why the people is looking for the extending the periodic table? The answer for this question is the theory of island of stability. What is this theory of island of stability says? This says that the nuclei with the atomic number 114 to 116 and the neutron number n is equal to 184 expected to have the longer half-lives compared to their neighbor nuclei due to their closed nuclear shells and providing the extra stability. Here I have shown the artistic chart of the island of stability. Now the most stable element as per the nuclear phenomena, that is the lead. Beyond the lead, so we are expecting the one more stable mountains, that is towards the element 114 to the 126 with the neutron number 184. Many theories, including the microscopic and the macroscopic relativistic theory, says that the atomic number Z is equal to 114 and neutron number 184 is found to be the most stable among these super heavy elements. And HFB and this relativistic mean field theory also says that so there is a chances of synthesizing the longer half-life super heavy nuclei in the atomic numbers 114, 126, and 120. Even in our predictions also, we predicted that the super heavy nuclei 114, 124, and 126 with the mass number 291, 312, and 314 are found to be most stable among the synthesized super heavy nuclei. So this is actually theoretical predictions. Actually, if we look into the different theories, so as I said, now the experimental limit is what, the 118. So there is a constraints on the availability of the suitable projectile target combinations to synthesize the element 119 and 120. This relativistic atomic many-body quantum theory says that elements can exist up to the Z is equal to 172. Bohr's theory says that we can extend the periodic table up to the 132. And quantum electrodynamic theory says that the periodic table can be extended up to the Z is equal to 170. But actual fact is, if you look into the production cross-section versus the atomic number, as this atomic number keeps on increases, this production cross-section decreases. In the Z is equal to 104, the cross-section is around the microbar. When it comes to the 118, the cross-section comes to the picobar, 10 to the power of minus 12 bar. Why this is? This is because of the smaller values of the fission barriers. So this fission barriers is around 3 MeV in the starting of the super heavy element limit. When it comes to the 118, it comes to the around 0.5, 0.4 like that. So if the fission barriers are very small, then that nuclei can easily undergo the fission. That is the one reason. If you look into the another reason, as this atomic number keeps on increases, the lifetimes also keeps on decreases due to the various factors like the Coulomb repulsion and other factors. So for the element 104, it is around hours and minutes. Its lifetimes is around hours and minutes. When it comes to the element 118, so it is in terms of the lifetime is in terms of the milliseconds. And the last super heavy element synthesized is in the year 2008, that is the 118. So after that, many attempts were found in the literature. So GSI used the fusion reaction of titanium and berkelium to synthesize the element 119. So Riken attempted the vanadium and curium. They conducted the continuous 90 days experiment and files to get the atoms. So this JNR Russians also, they did the experiments continuously around 120 days and they were not able to find the cross section. And again, similarly, this GSI and other laboratories also tried to synthesize the super heavy nuclear or element. They find difficult to find the number of atoms, even for the continuous experiment around in terms of the 90 years, 100 years, and the 100 days, 90 days, and 120 days. So the problem is actually a huge effort has been put up since 2009 to discover the element 119 and 120, but they were not able to find this element. The reason is we thoroughly studied the reason behind the failure of this fusion reactions, and as per our knowledge, we revealed the secret behind the failure of these fusion reactions to synthesize the super heavy element. And of course, it is the pathway for the discovery of the new elements. Here in this slide, I have shown the mechanism of synthesizing the super heavy element. Here, the projectile hits the target. Pre-capture stage formation takes place. During the pre-capture stage, there is the chances of undergoing the fission. That is, Coulomb fission. We used to call as the Coulomb fission. Once it crosses the pre-capture stage, it enters the capture stage. At that stage also, there is a chances of undergoing the fission. That is called as quasi-fission. And once it crosses the capture stage also, it forms a dinuclear system. And after the dinuclear system, the compound nucleus formation takes place. During the compound nucleus stage also, it undergoes the fission. That is called as fusion fission. This fission is the important threat for the formation of the compound nucleus. Three types of fissions. One is fusion fission, another one is quasi-fission, and the another one is the Coulomb fission. After once this compound nucleus sustains this all this fission stage, it forms the evaporation residue cross sections with the emission of the few neutrons, sometimes the 1 or 2 protons, sometimes the alpha particle also. Then that is called as the super heavy nuclei or the evaporation residue nuclei. So by studying the detailed experiments of the super heavy element synthesis, we constructed the 5 rules. Now it is familiar as the thumb rules for synthesizing the super heavy element. Our group consolidated all the experiments and we framed these 5 rules. First one is fusion of the 2 spherical nuclei yields the larger cross section. Second rule is the fusion of one partner, either projectile or target is spherical and other being the deformed yields the production cross section in terms of the picobar, 10 to the power of minus 12 bar. Fusion of 2 deformed nuclei cannot be produced the measurable cross section. This is what the mistake this different famous accelerators did, and they failed to synthesize the super heavy element. And fourth rule is the deformed evaporation residue as a super heavy nuclei have a better survival probability than that of the other spherical nuclei. Fifth one is very important. So the optimal beam energy for an allowed reaction with respect to the first 4 laws must be determined. That means the optimal energy is very important for the synthesizing the super heavy nuclei. That means at which energy we need to hit the projectile with the target. That is very important. That is the optimal energy. So these thumb rules for synthesizing the super heavy elements is published in the reputed international journal. After that, we extended our study for the last rule, optimal energy rule. I said the energy is very important. Energy at which this fusion reaction takes place is very important. And we verified this with the experimental reactions. We found that, the experiments were conducted at the higher energies, where this actual optimal energy is at the lower energies. That is the basic reason for the failure of these attempted fusion reactions. So we got the many experimental evidence, or you can call the proof for our optimal energy rule here. So in the year 2004, the element 115 was synthesized at the excitation energy 42.7 MeV. At that time, they found the cross section around 2.49 picobar. We framed the rule in the year 2022. We said, in our research paper, which was published in the Physical Review, and we said, if you do the experiment at the energy 34 MeV, we will get the 10 times larger the cross section. That is, instead of 2.49 picobar, we're supposed to get the 34.2 picobar. That is the one of our success of our theory. So this is the proof for our optimal energy rule. And after that, we found that we extended our study for the deformation compound nucleus formation probabilities. And we found that there is no systematic formula or systematic equation to calculate the compound nucleus formation probability for a given projectile and target combination. For that case, we formulated the compound nucleus formation formula, and that is published in a reputed international journal. And with the simple inputs of the projectile, target, and the energy, we can able to predict the compound nucleus formation probability, and that we compared with the available experiments, and it matches well with the experiments. This is also one of the success formula to produce the compound nucleus formation probability. So once the survival probability is also very important, because if you fuse the projectile with the target, the fusion cross section comes in terms of the millibar for the super heavy nuclei. When it comes to the production cross section, it comes in terms of the picobar, 10 to the power of minus 12 bar. That means, so the probability is very less. We need to predict that probabilities accurately. That is why we thoroughly analyzed the available all experiments and formulated the simple formula for survival probability for the compound nucleus formation. And with the simple, as I said, with the simple inputs of the atomic number of the compound nucleus, mass number of the compound nucleus, fission barriers, and separation energy, and nuclear temperature, this accurately produces the survival probability of the compound nucleus for the given projectile and the target at the given energy. So that compound nucleus formation probability, this is another formula, success formula, survival probability, which can able to produce the survival probability of the super heavy nucleus. After that, we extended our study for the systematics of the deformations. How this deformation mechanics or deformation parameters influence on the synthesis of the super heavy elements. In that manner, we thoroughly studied the experiments involved in the synthesis of super heavy elements, and we've constructed a systematics, and that systematics also published in reputed international journal, and we got an answer. So what type of the deformed nuclei we need to take for the synthesis of the super heavy nuclei, that is also involved in the included in the used in the literature, and now the people are using this formula for the experiment prior to the experimental studies. So as I said, three types of the fissions are. One is the Coulomb fission. Of course, the Coulomb fission we can easily eliminate, and another one is the quasi fission and fusion fission. This quasi fission and fusion fission are in this aspect, we thoroughly studied the systematics of the quasars which were involved in the synthesis of the super heavy element 119 and 120, and we clearly concluded which reaction yields a smaller value of the quasi-fission cross section and which reaction yields the smaller value of the fusion cross section. So this we published in a reputed international journal. This hindrance is a very important point for the study of the super heavy nuclei. As I said, this super heavy nucleus is highly radioactive. Here I have shown the two figures. In the left side, I have shown the lifetimes of the heavy nuclei. So if you take this thorium, its lifetime is around 10 to the power of 10 years. When it comes to the curium, its lifetime keeps on decreases. This is for the region. When we move on to the super heavy region, the lifetimes for the super heavy element to the this super heavy element 118, its lifetime is found to be in terms of millisecond. So within the span of the 10 to the power of minus 3 seconds, that atom exists and disappears and decays to the some other element through the alpha decay or the beta decay. So that is why this decay, the study of radioactive decay properties are very important in the this super heavy nuclear study. So usually this super heavy nuclei is considered as neutron-rich nuclei. What is this actually neutron-rich nuclei? So in the nuclear chart, there is two drip lines are there. Here I have shown upper blue line is called the neutron drip line, and here second one is called the upper blue line is proton drip line, and red line has shown the bottom, that is the that is the proton drip line. A neutron drip line is just a boundary and bind the extra neutrons. Similarly, for the nuclei cannot bind the extra proton. Drip line is called as neutron-rich nuclei. The nuclei, above the proton drip line, that is called as proton drip line. As I said, this super heavy nuclei is considered as the neutron-rich nuclei. These are all the super heavy nuclei are neutron-rich nuclei. So there is a probability of undergoing the alpha decay, cluster decay, and heavy particle decay. In the region of the super heavy nuclei, alpha decay is the dominance one, and cluster decay is the dominance one, and heavy particle radioactivity is the dominance one. Alpha decay means, the emission of alpha particle from the unstable nucleus. Cluster decay means the emission of the elements, the emission of the nuclei, which is greater than the alpha, that is C12, C14, up to the magnesium and phosphorus. All these elements can easily emit from the that heavy nucleus, that is the cluster decay, and some nuclei itself emits from this unstable super heavy nucleus, that is the heavy particle radioactivity. All these three types of the decay, that is alpha decay, cluster decay, and heavy particle radioactivity, is the dominance decay mode in the super heavy nucleus. So energetically favorable, and it is the dominant decay mode in the super heavy nucleus region. Whereas we cannot expect the beta decay in the super heavy region. Why? Because this beta decay is not energetically favorable. So because the Q values are found to be very small, negative, that is why this beta decay is not energetically favorable. So, and however, the Q values are positive in case of the proton emission, but because of the large Coulomb repulsion, so it is very difficult to emit the proton from the super heavy nuclei. That is why this proton emission is also unlikely, unlike dominant decay mode in the super heavy region. Whereas electron capture is not possible, because when a proton-rich nucleus wants to increase its neutron count, its super heavy nuclei are typically neutron-rich, so it is highly impossible to undergo the capture of the electron from the nucleus. That is why these three types of the decay is not possible in the super heavy nucleus region. So in this region, as I said, these lifetimes are in terms of the milliseconds, sometimes seconds, milliseconds, and the microseconds. That is why accurate prediction of the lifetimes are very important. In the literature, more than 30 formulas are available. More than 30 types of the models, formulas are available to evaluate the lifetimes of the super heavy nuclei. we systematically compared the values produced by all the formulas with the experiments. We found that only few formulas can produce the values close to the experiment, and we tried to predict the lifetimes better than that formula, and we successfully we constructed the that formula. And that uncertainties are very important. Uncertainties associated with that formula is very important, and that is reported in the literature. And apart from the empirical formulas, more than 12 models are available in the literature to study the radioactive decay properties, including the microscopic and the macroscopic. We systematically used the microscopic and macroscopic studies and predicted the lifetimes compared with the experiments, and we have shown that which model is exactly produces the experimental values. And that is also important for the prediction of the lifetime that is reported in the international journals. After that, we tried to construct the most accurate empirical formula to produce the lifetimes of the super heavy nucleus. In that direction, we successfully constructed the half-lives semi-empirical formula. Why we used to call this a semi-empirical means this involves the to construct the formula. We used both the experimental as well as the in some cases the theory. That's why we used to call this a semi-empirical formula. This semi-empirical formula easily produces the values close to the experiments than that of the available literature formulas. And also we thought, to predict the decay energies. Decay energies are very important for the study of the super heavy elements. We constructed the simple semi-empirical formula which can able to produce the decay energies in case of the alpha decay as well as the cluster decay, and we compare that with the experiments. It successfully produces the experimental decay energies. So after the calibration of the theory, we have constructed our own theory, our own formulas, and we used the most accurate models like the Coulomb and proximity potential model, CPPM, and the modified liquid drop model, MGLDM, and our own models, and we predicted the lifetimes. So we found this type of the variations. There is a sharp humps are there and peaks are there. So these are very important for the study of the nuclear structure in the super heavy region. And we found that some of the unusual drops, those are corresponds to the, that may be the evidence for the, signature of the new magic numbers also. In that direction, surprisingly, we found the evidence for the neutron magic number with the n is equal to 184. So in this figure, we shown the variation of the half-life with the neutron number. So for neutron number n is equal to 184, there is a dip which shows that it can easily undergo the decay. That's why we used to. This is a theoretical evidence for the neutron magic number. So n is equal to 184 from this cluster radioactivity studies. And we found the heavy particle radioactivity, especially in the super heavy element 126. So in the super heavy element 126, we found 3 nuclei can easily undergo the heavy particle radioactivity. That nuclei easily emits the particles like the carbon 12 and the nitrogen atoms as it is from the heavy nucleus, and we reported that in the literature. And the cluster radioactivity is also found in the super heavy element 120. And this 120, the region between mass number region between the 290 to 310 is very important. Why the people is now they are trying to synthesize the super heavy element 302, 303. So that comes in this region only. In that region, we systematically studied the radioactivity and alpha decay half-lives, all these things. We predicted the exact values. It will be useful for the experimentalist. So after that, systematically we studied all the radioactivity decay properties of almost all super heavy nuclei region between the Z is equal to 119 to 126, and we prepared our own nucleide chart, and we found that the sum of the super heavy nuclei like the Agnesian 122 and this 123 and 124, 126 can easily undergoes the cluster decay as and heavy particle radioactivities. And so that can easily emit the heavy nucleus as it is emit the yttrium nuclei and zirconium nuclei and krypton nuclei. So that is also reported in the literature. So if you look into the exact radioactive decay properties of the super heavy nuclei 119, so this is the nuclei. Now all the nuclear physicists are focusing to synthesize the super heavy element, this 119. So, and we predicted the possible decay chains and possible isotopes for this thing. And these decay chains are very important during the measuring the half-life, experimental half-lives, and that we reported. And this is the radioactive decay properties of the super heavy nuclei that is equal to 121. So here, the most probable isotopes are having the mass number between the 209 to the 304. This 209 121 super heavy nuclei may have the 2 alpha decay chain. After that, it ends with the spontaneous fission. And this is also having in terms of the microsecond. However, the super heavy nuclei 121 301 is also having the lifetime in terms of the microseconds. The lifetimes are very, very small here. And this super heavy nuclei 122 302 is the most focused super heavy nucleus by this acceleration physicist, because now in many places like the Riken laboratory of Japan and this Australian nuclear accelerator facility also, they are conducting the experiments to synthesize the super heavy nuclei 12302, and we successfully predicted the possible decay chains for this 12302. This is having the 3 alpha decay chains, and ends its life with this spontaneous fission, and it may have the lifetimes around 1.3 millisecond. And we systematically predicted the lifetimes as well as the decay energies for this nucleus, and this will be useful for the experimentalist. And this is the nuclear chart published by our group. So around 6-7 members, including the Tapan Nandi sir from the Inter-University Accelerator Center of the Delhi, we both grouped together, systematically studied the reactive decay properties, and we published our nuclear chart. This is the nuclear chart between the atomic number 104 to the 126. So here the cyan, all the maroon color, the boxes which are shown in the maroon color corresponds to the alpha decay. The boxes which are shown in the yellow color corresponds to the cluster decay. However, the boxes which are shown in the violet color is the spontaneous fission, and cyan color is the beta plus. Of course, some of these are energetically not possible. So some of these are showing the very, very small half-lives, and in the computation between different decay modes, the few shows the beta plus decay instead of beta minus decay. This is the nuclear chart published by our group. So coming to the detailed investigation of all the super heavy elements, the super heavy element 118 and 120. So we predicted this super heavy element 119 may have the isotopes between the mass number 275 to 325. Of course, out of that only the 3-4 isotopes may have the lifetimes in the milliseconds. We cannot able to detect the super heavy nuclei once its lifetime is greater than the microseconds. So these nuclei are having the lifetimes in terms of the millisecond. So that is why, so this can be easily detected through the experiments. So, and we suggested the possible fusion reactions to synthesize this super heavy element 119. For example, for this calcium and californium and titanium and curium and scandium and berkelium are most favorable reactions. And among that, the titanium and berkelium will be the most favorable reaction for the synthesis of the super heavy element 119. Vanadium curium is also predicted as the most favorable reactions for the synthesis of the super heavy element 119. So this is in this slide, just I have shown the slide shown by this Riken lab head. So this Riken people, accelerator people, the scientists are conducting the experiment to synthesize the super heavy element 119 through the reaction vanadium and curium, and they quoted our predictions in their presentations, and they used the reaction suggested by our team. So, and they're conducting the experiments, and we try to request the collaboration, of course, because of the many other problems we were not able to achieve the collaboration. Of course, this is the reaction suggested by our team, the vanadium and the curium. They quoted myself, Sridhar, and Ramalingam sir. We predicted that the cross section for that is around 4 femtobond, and they are trying to synthesize that super heavy element 119 through this reaction. We can say that this is one of the success of our team. And apart from that, we clearly explained why the super heavy element 120 was synthesized through the reaction iron and the plutonium. This American people, this Ganil laboratory, they tried to synthesize the super heavy element 120 through the reaction this iron and plutonium, but they were not able to find the atoms, because they conducted the experiments at the higher energies. We suggested that if we decrease the energies, there is a chances to get the atoms. So likewise, we predicted the possible isotopes for the super heavy element 120. It may have the mass numbers between 275 to the 330, and also for the super heavy nuclei 120 also. So we predicted the possible isotopes. It may vary between the 299 to 304, and we suggested that the vanadium and californium is the most favorable reaction for the synthesis of the super heavy nuclei 121. Likewise, for almost all the super heavy elements, we identified the all possible isotopes and also the corresponding decay chains. For instance, so we have shown for super heavy element 122. So these 6 nuclei are most possible super heavy nuclei. This may undergoes the 3 alpha, 2 alpha, and 1 alpha decay chains and ends with the fission. And this manganese and the californium will be the most favorable reactions for the synthesis of 123, whereas for the 122, chromium and the californium is the most favorable reaction for the synthesis of the 122. Likewise, for almost all the super heavy elements, from the 119 to 126, we systematically studied the possible isotopes and also the energy, possible optimal energies, and possible fusion reactions. All this we suggested. Experimentalists may use this thing, and as I said, this is center point of the island of stability. The super heavy element 126 is the center point of the island of stability. Out of this, we strongly concluded that this 126, 307, 318, 19, 320, and 23 to 326 are most probable isotopes for this 126, and this will be the center point of the island of the stability. And we systematically studied all the decay half-lives, all these things. So likewise, in the super heavy element work, we identified the possible isotopes, and the selected the suitable projectile target combinations, and suggested the exact energies, and we revealed what is the reason behind the failure of those fusion reactions, and we established the semi-empirical formula or empirical formula to predict the mass excess and fission barriers, deformations, compound nucleus formation probability, survival probability, half-lives, fusion barriers, and almost all the physical quantities. We systematically established the semi-empirical or empirical formulas. Now the people are using that formulas for the prior to the experiments. So we used to say our success is, we revealed the secret behind the failure of fusion reactions, which is important, and it is the pathway to discover the new elements, super heavy elements. I hope this super heavy element will be extended beyond the 118. So thank you, and this is our our research group. Almost 18 members are working with us in the nuclear physics group. So thank you, sir. And now welcome.
Thank you very much. Thank you very much, Dr. Manjunath, for a very informative presentation. Now there is time for some questions and answers. So anybody would like to ask any question, they may ask one by one. They may raise their hands and then ask questions one by one. Okay. Anybody would like to start? Okay, before the start, I have a few questions. You said that there is an optimal energy required for the formation of these super heavy elements or the reaction cross section.
Yes,
What is the reason for that? Can you explain, and how to get that optimal energy? Is there any formula to arrive at that optimal energy for production of super heavy elements?
Yes, sir. Actually, that was the big question till 2021, sir. Actually, after that, the people got an idea. Even we got an idea. Actually that optimal energy is the point where this barrier distribution and this quasi-elastic barrier distribution matches. That is the point where this we will get the evaporation density cross sections maximum at the point where this quasi-elastic barrier distribution QUBD is maximum and fusion barrier distribution is maximum. Using that, we have a simple formula to produce the optimal energy for all the fusion reactions.
Oh, you have a formula, okay.
Yeah, we have the formula and it is published in the physical reviews.
Oh, so how does it match with the experimental observation?
It is matching well with the experiments. It is matching well with the experiments. Now the people are using that formula. That is important, actually.
Very good. Professor Srikanta, I would like to ask a question. Yeah, Srikanta, you may unmute and ask question. Dr. Srikanta. Okay.
Yes, sir. Yes.
Please ask.
Sir, namaste, Dr. Manjunath.
Namaste, sir.
And it's a nice presentation. I have two questions.
Yes, sir.
In many of your slides, particularly in the last few slides,
yes, sir.
You have shown that we have studied the alpha decay properties of super heavy nuclei with Z equal to 120, etc., more than 120 also. So
Yes,
there are theoretical predictions, right? Because 118 is the heaviest element that has been detected, right? I mean, found.
Exactly, sir.
These are theoretical predictions, right?
Yeah, theoretical prediction only. As I said, sir, first we formulated our own theory, sir, based on the experiments. We extended that theory for the hypothetical elements 119 to 126.
And when it comes to heavy elements, is there any limit for this neutron-proton ratio? I mean,
that's what, sir. Different theory says the different answers, sir. This quantum electrodynamics theory says that up to 172 it can extend periodic table. And if you say this Bohr's theory, up to the 137 it may have, sir. Total 137. Different theory says the different answers. The experiments only says the correct answer for this question.
So I wanted to clarify cluster radioactivity. I didn't understand cluster radioactivity.
Yeah, cluster radioactivity means the emission of alpha particle from the nucleus is called the alpha decay. Whereas the emission of the nuclei, daughter nuclei, which is greater than the alpha, that is called as the cluster radioactivity.
So that is heavier than alpha particle, you mean?
Heavier than even the carbon atom as it is emitted from the nucleus, and this if you say nitrogen atom as it is emitted from the nucleus, that is experimentally studied, sir.
So it is spontaneous in the sense it wants to adjust the energy and requirement and things like that.
Yes, sir. That is the energy.
It's only to reach the stability, right? That's
yes, sir. Stability is actually it should be energetically favorable. Here the thing is how to decide the dominant decay mode is for a given nuclei. We used to study the almost all possible decay modes: alpha decay, beta decay, cluster decay, heavy particle decay, all these decay modes. We used to check which decay mode is having the shorter half-life and which decay mode is having the positive decay energies. Then that decay mode is considered as the possible decay mode. That is how we used to declare the possible decay modes.
Thank you, sir. Thank you.
Any question?
Yes, sir.
Do you have any kind of a formula for estimating the lifetimes of these super heavy elements? Empirical formula? Do you have?
Yes, sir. Yes, sir. Yes, sir. Sir, in literature, as I said, that is that in one of this presentation slide, I've shown many more than 20-25 formulas are there. So we validated which formula produces exact lifetime, and we found that some uncertainties are there. So after that, we constructed our own formula. And more than 20-25 formulas are available in the literature. sir.
ಸರಿ ಅನ್ಮ್ಯೂಟ್ ಆಗಿದೆ. ಓಕೆ ಸರ್, ಓಕೆ ರೈಟ್ ಸರ್.
Yes.
Any other questions?
Sir, Somshekar is asking.
Professor Somshekar, please ask. Unmute. Mute ಆಗ್ಬಿಟ್ಟಿದೆ. ನಿಮ್ಮ ಇದು ಸ್ಪೀಕರ್. Microphone, please ask. Unmute.
Sir, Somshekar.
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. You have to unmute.
ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿ ಸರ್, ಸೋಮಶೇಖರ್.
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಅವ್ರಿಗೆ. ಅದೇ ನಾನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ, is not able to unmute. ಮ್ಯೂಟ್ ಆಗ್ಬಿಟ್ಟಿದೆ ಇದು. ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
Yes.
ಪ್ಲೀಸ್ ಅನ್ಮ್ಯೂಟ್. ಮ್ಯೂಟ್ ಆಗಿದೆ. ಸೋಮಶೇಖರ್ ಮ್ಯೂಟ್ ಆಗಿದೆ. We can't hear you. Okay, anybody? I don't know who are the other people. Is not able to unmute. One small question I have. Are you able to hear me? Okay. One question is, all the time you have to make use of very heavy projectiles in your experiment, isn't it? So,
Yes, sir.
so is it very difficult to produce heavy elements with high energy, or heavy projectiles like iron, nickel, all those things you are using for fusion, isn't it?
Yes, sir. Exactly, sir.
Exactly. Is that a difficult problem, or can it be done easily in?
It is difficult, sir. Actually, it is difficult. Actually, in India, it is difficult to synthesize the element. Actually, that is why that Riken of Japan and the Russians, Darmstadt, Germany, and the Ganel laboratories, those reputed international accelerator facility.
Only they can do it.
There is a heavier beams, and we can able to do the experiments. Now it is in India. It is not possible.
Yeah, that's what I was going to ask. We have this Indian center, the inter-university center. So they are not able to produce. They are not able to produce heavy projectiles, I think.
Yes, I tried to submit this beam time 2-3 times to this USA. They may not able to accept that. Reason is the same thing. The heavier projectiles are very difficult.
Yeah, so they are not able to produce heavy projectiles.
Heavy projectiles. Yes, sir.
Professor Nagaraj, you want to ask any question? Rudaswamy?
Of course, this.
Hello.
Sir, ಇವಾಗ ಅನ್ಮ್ಯೂಟ್ ಆಯ್ತು, but there was some problem earlier. Now it is possible.
Okay, please ask. Okay.
Dr. Manjunath.
Phone off
formula, empirical formula, which you have formulated. So did international committee accepted? What is the status?
It is published in the reputed international journals only, sir. Physical reviews and this Journal of Physics G. Now people are using, sir, citations. That's citations and this acceptance of that paper in the reputed journal will be evidence for this acceptance of the scientific community. Sir.
What is the latest element synthesized? Super heavy element synthesized.
Sir, in last is not in 2008 actually 118 was synthesized. After that the huge effort is going on. Probably by the end of this year or in 2026.
ಉದಯ್ ಶಂಕರ್ಗೂ ಹಾಗೆ ಆಗಿದೆ. ಈಗ ಆಯ್ತು, ಅನ್ಮ್ಯೂಟ್ ಆಯ್ತು. ಉದಯ್ ಶಂಕರ್ಗೂ ಅದೇ ಸಮಸ್ಯೆ ಆಗಿದೆ. ಸೋಮಶೇಖರ್ಗೂ ಆಗಿರ್ಬೇಕು ಅದೇನೆ.
Okay, I will try.
Okay.
So Japanese is able to synthesize this element, sir. Probably next year. 2026.
These elements are most radioactive elements,
Exactly.
Highly radioactive.
Exactly.
So, can they be considered as a stable element? Though they are radioactive, highly radioactive. Can they be considered as stable element, can they be included in the periodic table? What is the...
For the inclusion of the element in the periodic table, it need not to be stable, sir, actually. Up to the 118 was included. The super heavy element 118 is included in the periodic table. Its lifetime is around millisecond.
Oh, even millisecond lifetime, could be considered,
Yes, sir.
to include in the periodic table.
Yes, sir. Yes, sir. Now the people are expecting the this 126 may have the lifetimes in terms of minutes, sir. Actually, that is why the people are struggling.
If the lifetime is very short, how to detect and recognize such elements?
Yeah, the detectors are these decay chains. By detecting the decay chains, sir, alpha detectors, the decay chains. That is why the prediction of decay chains are very important. In our slide, our studies, we successfully predicted the decay chains.
Okay. Anybody? Any other questions? 1 minute, please wait. Any other questions? Okay.
Unmute ಆಯ್ತು ಸರ್.
ಹೇಳ್ತಾರೆ ಮಾತಾಡಿ.
ಸರ್ ಏನಿಲ್ಲ, ಈ ಸರ್ ಮಂಜುನಾಥ್ ಸರ್ ಅವರೇ, ಈ ಸೂಪರ್ ಹೆವಿ ಎಲಿಮೆಂಟ್ಸ್ ಏನಾದ್ರು ನ್ಯೂಕ್ಲಿಯರ್ ಮೆಡಿಸನ್ ಗೆ ಕಾಂಟ್ರಿಬ್ಯೂಟ್ ಮಾಡಿದ್ಯಾ ರೀಸೆಂಟ್ ಅಲ್ಲಿ? ನ್ಯೂಕ್ಲಿಯರ್ ಮೆಡಿಸನ್ ಗೆ ಏನಾದ್ರೂ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ ಆಗಿದ್ಯಾ ಸೂಪರ್ ಹೆವಿ
ಹೆಲ್ಪ್ ಆಗುತ್ತಾ ಅಂತ? Why do you do this?
ಅಥವಾ ಆಗಿದ್ಯಾ ಲಾಸ್ಟ್ 2 decades?
Okay, sir. Sir, actually, these are highly radioactive. Meanwhile, larger value of decay energies are there. Larger values of decay energies are there. When curium was discovered by the Madam Curie, at that time the people may not be aware of the uses of
users. Okay.
So this because of the larger Q values, this may find the application in the radiation physics and the radiation process.
ಸರ್, ಹಾಗಾದ್ರೆ ರಿಯಾಕ್ಟರ್ ಯೂಸ್ ಮಾಡಬಹುದಾ ಸೂಪರ್ ಹೆವಿ ಎಲಿಮೆಂಟ್ಸ್ ನ?
One by one. Okay.
ಸೂಪರ್ ಹೆವಿ ಎಲಿಮೆಂಟ್ಸ್ ಅಂತ ಹೇಳಿದ್ರಲ್ಲ, ಈಗ ಯುರೇನಿಯಂ 235 ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ನ್ಯೂಕ್ಲಿಯರ್ ರಿಯಾಕ್ಟರ್ ಅಲ್ಲಿ. ಹಾಗೇನೆ ಈ ಸೂಪರ್ ಹೆವಿ ಎಲಿಮೆಂಟ್ಸ್ ನ ನ್ಯೂಕ್ಲಿಯರ್ ರಿಯಾಕ್ಟರ್ ಗಳಲ್ಲಿ ಯೂಸ್ ಮಾಡಬಹುದಾ ಅಂತ?
Sir, I think it is not possible, sir, because so in nuclear reactor, uranium is used as a fuel actually.
Yes.
So this uranium 235, it's having the lifetime in terms of years.
Yes.
That is not possible, but it will be useful for the radiation physics. Radiation physics like the ಕೋಬಾ ಇದು ಟ್ರೀಟ್ಮೆಂಟ್ ಗೆ, ಕ್ಯಾನ್ಸರ್ ಟ್ರೀಟ್ಮೆಂಟ್ ಆ ತರದಕ್ಕೆ ಯೂಸ್ ಮಾಡಬಹುದು ಅಂತ.
ಟ್ರೀಟ್ಮೆಂಟ್ ಗೆ ಆರ್ಟಿಫಿಷಿಯಲ್ ರೇಡಿಯೋ ಆಕ್ಟಿವಿಟಿ ಲೈಕ್ ಹೆವಿ ಅದರ್ ಲೈಟರ್ ಎಲಿಮೆಂಟ್ಸ್ ಆಲ್ಸೋ ವಿಲ್ ಬಿ ಯೂಸ್ಡ್ ಅಲ್ವಾ? ಆದ್ರೆ ಈ ಹೆವಿ ಎಲಿಮೆಂಟ್ಸ್ ಎಕ್ಸ್ಟ್ರಾ ಬೆನಿಫಿಟ್ ಏನಾದ್ರು ಇದೆಯಾ ಕಂಪೇರ್ ಟು ದಿ ಲೈಟರ್ ಎಲಿಮೆಂಟ್ಸ್ ವಿಚ್ ಆರ್ಟಿಫಿಷಿಯಲ್ ಎಲಿಮೆಂಟ್ಸ್ ಅಂತ ಮೇಡಮ್ ಕ್ಯೂರಿ ತೋರಿಸಿದ್ದಕ್ಕೂ ಇದಕ್ಕೂ ವ್ಯತ್ಯಾಸ ಏನಾದ್ರು ಇದೆಯಾ?
ದಟ್ ಇಸ್ ವಾಟ್ ಅದನ್ನ ಹೇಳ್ತೇನೆ ಸರ್. ಈಗ ಲಾರ್ಜ್ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಡಿಕೆ ಎನರ್ಜೀಸ್. ಸೊ ಇಫ್ ಯು ಟೇಕ್ ದಿ ಡಿಕೆ ಎನರ್ಜಿ ಆಫ್ ದಿ ಕ್ಯೂರಿಯಂ, ಸರ್, it is around 7 MeV, 8 MeV, like that. Here it is around 16 MeV, 17 MeV, 18 MeV decay energy is there. That energy is important, no, sir. Even the lifetime is milliseconds, the decay energy is in terms of 15-16 MeV. You will get the decay energy double of this curium.
Okay, sir.
Any other question? Okay. Any other question?
The existence
Good morning, sir.
Sir, good great party.
Super elements can be used to determine the age of the plants. Paleontologists can, make use of these super heavy elements depending upon their half-life, of course.
Sir, and that I'm not sure about, madam. Actually,
they are all very unstable, madam. So, very unstable.
No, depending upon the half-life.
Yeah, I'm not sure about this thing.
But it will be too short, millisecond, microsecond, like that.
Microseconds. It is not possible, I think. So, but in astrophysics, it will be useful for the in astronuclear physics, it will be useful.
Okay. Any other questions?
Yeah, can I say?
Yeah, please. Okay, sir.
Uday here. Can I say, Kagli sir? Can I say?
Yeah, please do. Please go.
Manjunath, thank you very much. I am an astronomer, So to me, it is a completely new field, but you brought out your points of view very well. And I'm also very thrilled that sitting in a place like Devanahalli, you are able to do so much of work with your colleagues. First of all, my hearty congratulations for the wonderful talk and for the wonderful work that you have done.
Thank you very much. Thank you, sir. Thank you, sir.
Heaviest element astronomically people have seen. You also just now mentioned nuclear physics. So I just, excited to ask that question.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Sir, the existence of these super heavy elements are observed in these galaxies.
I see.
That is important.
Any specific reference you have? I mean, like in mind or any observations? It is observed in what? Optical, radio, or in multi-wavelength astronomy? Where does it been seen?
Yeah, it is there, sir. But my interest is to just create.
Yeah. No. I appreciate Manjunath. You have done a wonderful job of estimating the probabilities of formation of such super heavy elements and all that. It came out very well in your talk. Thank you. I'll also dig the reference and look at them. Thank you,
sir. Thank you.
Dr.
Wonderful
Manjunath,
Okay.
Yes, sir.
Indirect detection of super heavy element, don't you think that it is an hindrance to accept the existence of super elements? You followed my question.
No, sir. Please, sir.
Indirect detection of super element, you mentioned,
Yes, sir.
don't you think that it is an hindrance to accept them as
It's not indirect measurement, sir. It is not indirect measurement, sir.
Existence of super element?
So what his question is, if they are detected in astronomical bodies, is it a hindrance? Definitely not. It shows that such super heavy elements are possible. They can be produced. So that
But
is support of the theory. It is in support of the theory. It is not against the theory. Okay. We want to Professor Nagaraj, please.
Yes, sir. I am here.
Yeah,
Yes,
please.
Dr. Manjunath, you have done wonderful work. Even though you are in an undergraduate college, you have done an excellent work, like Professor Uday Shankar has already mentioned. Thank you very much. You have accepted our invitation and you have given your work. And in fact, you have presented very beautifully and about your work. So thank you very much. We wish that we will go ahead with more than what you have got, like 121, 122, something like that. So wish you all the best from our KPA. And I wish all the members, I think some invitees are also present in this meeting from KPA, Karnataka Physics Association. I thank all of them. And I thank our KPA members. And I should thank Jnanadhara, Dr. M.K. Raghavendra. In fact, he is providing the Zoom platform almost every Sunday. And we should thank Professor B.A. Kogli and Rudraswamy, because I think through Rudraswamy, you have contacted the KPA. So thank you very much for all.
Thank Raman also.
Thank Raman also for making that YouTube connection. Okay. So thank you one and all. And I think Professor Kogli has
next week. Next week there will also be another online talk. So please come and join that meeting next week, next Sunday. Probably it will be on artificial intelligence and how it can be used in various fields. So therefore, please join next week at the same time. Thank you very much. Thanks to the speaker and all the participants. Now we are leaving the meeting, all of you.